Hello, it's Linton again. It's the Saturday the 14th of July 2018. We got through another Friday the 13th without anything remarkable happening. Um, yeah, so welcome. The This is the third part of how to make your own little universe or a very big universe. Um, and eh, Now, we're trying to make a universe using just weirdness as little as possible. Anything you can say, that's magic, um, counts against us. And we've, so far, I guess, done only asked for a moment of magic once. Uh, these smiley faces there, that means, okay, good, we just got rid of a magical thing. If you want to see the key that relates the magical things that we have disposed of to the place we dispose of, just go to nobabies.net and run down to the Kim lecture and open that, and you'll see they're all numbered, but uh, that would be intrusive for this presentation. Okay, once we started that, we got a bunch of big bunch of stuff together. Thanks to some hand waving, but only one piece of magic, that was a neutron. And the whole thing, if there's enough of it, crowded enough, it collapses, and that's called what we could call it, the big crunch. Um, uh, and it's the Big Bang going in reverse, of course. Um, Once the crunch starts, nothing can stop it because to stop it, you'd have to have physical strength within the structure that's collapsing to hold it out. Um, and if something is stronger, it conducts vibrations faster, and the uh, if it's strong enough to hold the universe up just by physical pressure, eventually it takes so much strength that um, having vibration go through it would exceed the speed of light, which can't be done. Um, so once the runaway collapse starts, nothing uh, can stop it by sheer strength. Um, since the matter is pulling on space, um, as well as other matter, we're not surprised to see that the looks like space is falling in on itself. You remember the uh, the gravity well. Things in the gravity well are slower because this the space through which the photon travels is basically being stretched. Either the laws of nature came with a neutron, or the fact that the universe was going to have to produce life means the laws of nature had to be suitable for life. That's called, I think, the third anthropic principle or something. And it has been discussed and begins to feel a little bit like it might be magic. Let's just stick and say the neutron brought those laws in and not at this point say that the laws were deliberately fine-tuned. Now, if you take a universe that contains a photon and warm the particle um, and change the size of the universe Oh, it's be cooling the particle. Okay. Got a universe, got a photon. Expand the universe, you expand the photon because the photon is traveling in space. Stretch the space, you stretch the photon. That doesn't warm it. Cools whatever's in it. Um, so the in here, which is within our collapsing zone, is if it were being stretched, the photon itself would be being stretched, being a wave, and the information required to specify the photon, or as it were, the information content of the photon, um, uh, the energy equivalent of knowing where um, the photon is, um, and that changes because the temperature temperature of the photon uh, fell. All right, so space, photon, stretch space, photon stretches. No change in the amount of information to specify the photon. The photon's bigger, the space is bigger, volume of distribution photon divided into the space is constant, right? So it's all reversible. But something's missing. A particle of matter, a solid particle, you know, our friend the neutron, it's different. If you look at the energy of a particle in a gas, the I mentioned if you want to know more about the information content of a particle and the what that means physically, then the thing to Google is Maxwell's demon. It'll tell you what you want to know there. All right. Particles of matter are different. If you look at the energy of particles in a gas, they're distributed along a curve, so the lower energies have the most particles. So let's take okay, I have to give you the punchline of a joke that took some air. If you gathered that air up and stuck it in a jar, there's a little bit of a that line's supposed to be dead vertical. It's just my limited use of the computer's graphics. It should be vertical here and over 0, and then this goes out to about horizontal. All right. By frequency, I mean the number of particles at that temperature. Temperature and energy, of course, makes the same thing. Energy there is what's the energy of any one particle. So if we grab a particle at random, it could be anywhere in here, but if we grab a particle and say, okay, we want to have this particle have certain amount of energy. How many of them are there? Well, the lower you make the energy, the higher the frequency of occurrence of a particle of that energy is. And up here, within sniffing distance of absolute 0, that's the highest frequency, the most likely single energy of an atom is 0. Got that? 0 is the one most likely energy, and as the energy increases, the number of particles at that energy level falls off and then levels off. The way out here, we got one particle has all the energy. That's not going to happen very often, but you're not going to go past that. So that's a finite number, and that, when you get to zero, that's your highest energy. Okay. At absolute zero, these particles have no energy. Therefore, the information that specifies their location is zero. That means the location is indeterminate, absolutely indeterminate. So remember, the higher the temperature, the better specified and localized an object is, the more the energy of knowing where it is. At absolute zero, that particle could be anywhere. Got that? At absolute zero, anything, any atom bouncing around, if it's at zero energy, it is at indeterminate location. All right? So this would be the arrangement if the whole gas were at absolute zero. All the particles are sitting here, and it's not infinite, it's just all of them, and no particle has any energy at all. All right, so that means those particles at zero energy are effectively located at random anywhere in space. And that doesn't just mean anywhere in the universe, the in here part of what's collapsing. It could be out there as well. And out there has to be a lot larger than in here. So the chance of it being in here at all is vanishingly small. Got that? Anything that hits zero, here. There. That bunch of gas is at zero, we're saying, and that means it bubbles out of the universe. Gone. The man came, the phenomenon is called Hawking radiation because Stephen Hawking, who's probably the most famous recently living scientist, he worked all the math out. He said, look, these atoms will simply bounce out of a black hole. It's called Hawking radiation. No one's ever seen it, but nobody doubts its existence, except, of course, except me, really. But his math is above reproach. So, if we go back to here, those things there are going to bubble outside of the our bottle of air at some rate specified by Hawking radiation. Now, Hawking phrases it in terms of quantum uncertainty. He's saying, oh, well, there's quantum uncertainty, and from time to time, an atom will be just outside of the bottle, or the black hole, and then if the universe is expanding, it'll probably drift away, and so your black hole will slowly boil away. That makes certain predictions have not been fulfilled. But the Hawking radiation calculation is above reproach. So sorry, believe it. Believe that the math has been worked out for that. All right, some guys, very clever men, working in a lab. They took a very cold gas, well, you know, our, come on, they took a bottle of gas, chilled it way down, and then using lasers like they were tweezers, they had all these atoms bouncing around here, very low energy, not many of them. Well, it would be frequency would be, be something like this, almost zero. Now, if they were all absolutely zero, so if you had a sample, everything in the sample has zero energy, you have high frequency at zero energy. There, right? Well, they had them not quite like that, it was about like this, and then they managed to take the atoms and raise their energy level a certain amount, all of them, right? So they pulled all these atoms and stuck them here. Now you have a high frequency, which is all of the atoms in the sample, at a moderate energy. So instead of that curve looking this way, the curve at the extreme kind of looks this way, right? You got that? So usual curve describing temperature, curve is upside down, so the temperature is negative, right? And they said, look, we've got negative temperature. Oh, everybody says, oh, cool. Well, in order to get, now these things didn't jump over there by quantum uncertainty. They were grabbed and pulled with a physical device, with lasers. So the sample, having gone from positive temperature to a negative temperature, had to have gone through zero temperature at some point. And that means the sample okay, distribution upside down, whole lab, so the whole lab should have zipped off to out there. Everything in the laboratory should have suddenly, when it hit absolute zero, should have been, its location should have been so indeterminate that essentially all the atoms turned up outside of the known universe, scattered totally at random, unthinkable light years between each one. All right, but the lab didn't disappear. Not even the sample disappeared. Not even a single atom in the sample disappeared. So there is information in the location of a particle that is independent of its temperature. Bingo, solid. Sorry, can't get around that. And that is totally against what the physicists teach, which is that that's the basic second law of thermodynamics. The one thing they absolutely believe is that the location of a particle the energy equivalent of knowing where a particle um, is a fixed amount. But no, there's something left even after you've considered the temperature. All right, so, but of course, you knew it had to be true. According to the curve, most likely temperature is zero anyway, even without clever men with tweezers playing games. Any sample of any physical object, the atoms rattle around. Most likely temperature is absolute zero. Most likely location is outside of the universe. The whole physical contents of the universe should boil away on the PDQ. So as in here, collapses, energy piles up. There's no quantum model because quantum uncertainty only happens in reverse time. Okay. That's actually a new point. All right. All right. Quantum uncertainty, as calculated by Hawking, only happens in reverse time. That's why the universe seems so smooth, I think. Now this is an obvious one. This is a gimme. With the universe as we've built it, there's no difficulty having orderly systems like life build up because in forward time, that is, as we going from Friday, Thursday, Wednesday, moving that direction through time, order automatically builds up. So there is nothing remarkable about orderly systems, like folks, or anything else orderly. It's gonna build up because as the universe collapses, nothing can escape. Order is the equivalent of energy, is the equivalent of matter. Everything gets compressed. Order builds up because it can't get out. Maybe some gets turned into energy. Maybe some of that gets turned into matter, but the order is always being forced upward. Just like in our present understanding, order is always being reduced, which leaves you a serious problem explaining why there's life. Since the temperature independent information about matter, it is real information, and since information equals energy equals mass, which has gravity, dark matter is exactly what you'd expect. We have a universe in which matter is located by some kind of information that has a mass equivalent. So you're going to have mass-like material which follows the distribution of ordinary matter, and this mass-like material, we'd be able to see it. We'd call it dark matter. Okay. Now, if we were out there watching the universe collapse, we'd see gravity building up while which means time is slowing down. From in here, we look out into space, we see the universe when it was more collapsed, right? All right, so the universe is doing this. We look from the outside, it's shrinking. Looked at from the inside, we think it's expanding, or at least most of us do, not I. But when we look back, look out into space, we're looking back into time, and things were moving slower because things move slower down a gravity well. And so it looks like the acceleration of the universe is accelerating. Physicists call it dark energy. It ain't so. You don't need that. So there's another piece of magic they throw at you. You say, no. Just recognize that you could, in principle, look at the universe from the outside, the in here universe, and you don't need anything spooky quite yet. But we're going to get there. All right, well, we'll have our second piece of magic. And we will call this second piece of magic a doohickey. And this is a picture of a doohickey. No, it's a wooden spoon, but it kind of has a face. So we're going to call that our doohickey because there's no other representation of anything remotely resembling a doohickey out there. And this will be this will wrap it up for today. Here's our doohickey, and what it is some object, physical or whatever. It has a memory which is not always perfect, and it is not always available to consciousness. It is conscious, and it is capable of abstract reasoning. If you've had a philosophical term, you might say those are just three ways of describing the same thing. Okay, go if you like. But the doohickey should be familiar because it's your personality. You remember things, but imperfectly. You can do abstract reasoning, and you're aware of yourself. So all I ask for is one of these things. Since you're one, you can't deny that they exist. But make no bones about it, it is very spooky. This is very close to being magic. Like the worst of modern science. All right, let's see here. I think we'll call that it for today. We'll go ahead and see what the implications of the doohickey are next time. So take care. Feel free to play this over and over again until you understand it. And feel free to drop me a line, info@nobabies.net, if you've got any questions. You might have to wait a few days because I don't check my email that often. So take care. Best of all.